Okay, now we will now, having characterized relative ages and absolute ages, we will now shift to a different field, and I will talk to you a little bit about igneous petrology. This essentially, as you have known from before, that igneous rocks are born of fire. So something in the earth melts, and this melts once they are formed. The density of the melts are 10% less on an average, 10% less than the rocks from which they are melted. So what happens, these melts, when they are formed, they start to ascend. They try to move up through the crust. But that's a very difficult process because rocks are very solid and moving up isn't very easy through a rock strata which is tens of kilometers or even hundreds of kilometers thick. It's not easy to move. How it moves, I think that's a different question that I don't wish to address here. It's too complicated for you at this moment of time. But what I would like to emphasize is that two options happen. Either when the melts are moving up, then the melts come into a domain, because as we move up, the temperatures decrease and so does the density decrease. So what happens? Many of these melts, when these melts move up, they come into colder zones. So what happens? They cool themselves. So what happens? These melts, when they are formed, when they cool, they crystallize minerals during cooling. And then they are called melt plus crystal is equal to magma. So when you have melts, you always have these naturally forming melts, these magmas, because there's always some little crystal in these melts. So when these melts move up because of buoyancy, then they will move up as far up to the zone of neutral buoyancy. They will move to the zone of neutral buoyancy, above which they cannot move. So then the melts needs to crystallize at the place where it meets the zone of neutral buoyancy. But sometimes what happens, and these rocks which cool below the Earth's surface, they are, if you remember, we call it plutonic rocks. These are called plutonic rocks. But sometimes what happens as the rock moves up, it sometimes connects with some fissures and cracks that reach up to the Earth's surface. And many of these magmas then gush upwards and they go out of the Earth's surface and they spread themselves on the surface, and these magmas are now called lavas. So when these lavas are there and they come in contact with the surface temperature of 25 degrees centigrade, then of course they cool very, very rapidly. So the chances of forming crystals is greatly reduced, and you produce what is called very glassy rocks, supercooled liquids, very glassy rocks with few minerals, and these are called volcanic rocks. Now we will come to the question, why do rocks melt? That's the first thing that we need to ask ourselves. Why do rocks melt at all? How do they melt? How do they crystallize? What are the ways in which they do it? And this would be our topic for several next presentations. So we will start first with the question, why do rocks melt? Now, as I said one thing, before we go into the topic, as I said one thing, that rocks are formed, we will go to that later on, rocks are formed because of, they are made up of, they are basically polymeric chains. They are polymers of what is called SiO4 tetrahedra. They are polymers of SiO4 tetrahedra. So what happens, these, like most polymers, these occur in isolated SiO4 tetrahedra, or they form as short chains of SiO4 tetrahedra, long chains of SiO4 tetrahedra, and the major building block, the SiO4 tetra. You can have branched polymers, and you can have whole configuration of this SiO4 polymers. So more the polymorphs are attached, the melts and the magma, they become more viscous. So they become less capable of flow. But when the polymeric SiO4 tetrahedral chains are broken down, then what happens is they become less polymeric and therefore capable of flowing faster. We will come to some of these topics later on a bit. But before that, let me tell you why we are talking of SiO4 tetrahedra. It is because silicon and oxygen, these are two of the most, along with aluminium, these elements, oxygen, silicon and aluminium to some extent, these are some of the dominant elements of the Earth's crust. And below Earth's crust, below the Earth's crust, you have the monovisic discontinuity, and below the monovisic discontinuity, you have the mantle, and even for the mantle, parts of the mantle, silicon and oxygen form a dominant component. That silicon, oxygen, aluminium constitute more than 85% by weight, 85% by weight of the total number of elements on the Earth's crust. By way of volume, silicon and oxygen constitute more than 90%, by volume of the crust. So essentially, these two elements form the major network of rocks and magmas, silicon, oxygen. Now, looking at it just very simply before we go, silicon and oxygen, the ionic radius of silicon is about 1.42 angstrom units. Very simplified, we are not going to much more complication. What will happen if it's ionic covalent? We will not go into that. Roughly, silicon ionic radius is about 1.42. Sorry. 0.42 angstroms. 0.42 angstroms. And oxygen is much bigger in volume. It's about 1.40 angstroms. So, if you had a silicon and an oxygen, and they were ionically bonded, so that means if you can conceive a silicon atom, 1.40, a oxygen 1.40, let's say we arrange oxygen atoms like this, 1.40, 1.40, silicon oxygen. Here you see a small space where you can accommodate a smaller ion, which is silicon, 0.42 angstroms. So you have what is called silicon-oxygen bond length. Ideally, if silicon and oxygen were behaving in a very ionic way, and that silicon and oxygen behaved as incompressible spheres, touching one another, then if you add them up, silicon-oxygen bond length should be equal to 1.82 angstroms. Silicon-oxygen bonds together, if they were incompressible solids, they would form about 1.82 angstroms. But if you measure the silicon-oxygen bonds in silicate minerals and manganese, you will see the bond length, silicon-oxygen bond length, roughly equal to 1.64 angstroms. It's not 1.82 angstroms, it's 1.64 angstroms. Why? It is because silicon and oxygen does not behave as an ionic bond. They behave as a covalent bond. So the oxygen and silicon clouds, they overlap and go inside. So it's not 1.82, it's 1.64 angstroms. So this tells you that the silicon-oxygen bond has strong covalency. Now this covalency, as we will see later at the moment, this silicon-oxygen bond covalency, it is about 60% covalent and 40% ionic. The SiO4 bond, this is 60% covalent and 40% ionic. So essentially, properties of covalent elements dominate in the silicon-oxygen bonds. Have you understood? So, say for example, if there are very perfect covalently bonded compounds, they would have high melting points, they would have high boiling points, they would be insoluble to water. They would be highly refractory in nature, and there would be strong directional properties. Have you understood? So, if this is so, that it is 60% covalent and 40% ionic, and the earth and the mantle is composed largely of SiO4 tetrahedra minerals and metals are SiO4 tetrahedra, then you must imagine certain things, that there will be poor electrical conductors, they will be poor heat conductors, they would be insoluble in acids, greatly insoluble in acids, they should have strong directional properties. So our earth, the crust and the mantle, have these properties. At the same time, there would be some amount of ionic character in our rocks and in our magnets. So I don't know whether you know what is coordination number. Coordination number is something here, I can tell you from here. So in a coordination number, a particular cation is surrounded here, for example silicon, let's be specific with that. It's surrounded by 3 oxygen, nearest neighbor oxygen atom. So here in this case, the coordination number is called 3. I'm sure that some of you would recollect what I'm talking about. This about Linus Pauling. If you remember, a recipient of 2 Nobel Prizes, Linus Pauling was talking about bonding and coordination number. In this case, this very case, N is equal to 3. But what happens is, our SiO4 tetrahedra, and we will go into this in some detail later on, but for the moment, our SiO4 tetrahedra looks something like this, where you have 4 oxygen atoms touching each other, 4 oxygen atoms. So like if you have a table tennis ball, ping pong balls, you place 3 on the board and 1 at the top, and that's a tetrahedron. So it's called an SiO4 tetrahedron, where inside here there is the small silicon atom of 0.42 angstroms surrounded by oxygen atoms which are 1.40 angstroms, as we have talked about. So essentially, this atom is SiO4 4 minus, SiO4 4 minus, and the coordination number is 4. This is the coordination number 4. Have you understood? So say for example, I can just quickly give you an example. Let's have a cube. Let's have a cube. And let's assume you can have 8 oxygen atoms. 8 oxygen atoms. 8 oxygen atoms. Or the 4 whose centers are located at the 4 vertices of a cube. Or 4 at the top and 4 at the bottom. They touch one another, and the centers of those spheres coincide with the vertices of the cube. So inside it, where the 4 long diagonals intersect, there will be a small cation. And its size will be determined. This is what is called Ra by Rc, which is Ra is the radius of the anion, and this is called the radius of the cation. This is called radius ratio. So inside, in this long diagonals where they intersect, there will be a small cation which lies at the center, surrounded by 8 oxygen atoms. And then the coordination number becomes 8. And this is called a cubic coordination number. This is called a tetrahedral coordination. And similarly, say for example, you can have a situation where so there will be 1, 2, 3, 4 oxygen atoms, one at the top, one at the bottom. That means a tetrahedral placed one above the other. And here inside you will have a small cation, and we can find out the Ra by Rc value. So this is what is the coordination number. It is related to something called the radius ratio. So you have 2 terms now, radius ratio and coordination number. These are the two important points that I would like to make. Why I am saying this is because SiO4 tetrahedron, this tetrahedron is not exactly a perfect tetrahedron. In crystals, in minerals and metal, the coordination number is 4.3, especially in melts. SiO4 melts. The coordination number, silicon oxygen coordination number is not exactly 4, it's 4.3. So we have several informations. The SiO4 tetrahedron has 4 negative charges which are not bonded. Here you see for every oxygen it is bonded to a silicon. So silicon 4 charges are neutralized by the 4 oxygen, but then 4 other charges of oxygen are set free. So you have SiO4 4 minus. They have 60% covalent, 40% ionic bonding. Their coordination number is 4.3. So this is the structure of the minerals and the metals. And more polymeric it is, the more viscous is the melt. And the less polymeric the melt is. That means if you have elements that can break the polymeric chains, then you will have melts that can flow easily. Okay, so now we go to the fundamental question as to why do rocks melt. We will understand it geometrically a bit. Right. And the question here is, why do rocks melt? I draw a figure here. This is temperature and this is pressure. That means depth. P is equal to H rho G. The pressure exerted at any point is equal to the height into the density into the acceleration into depth. Now, there are two graphs to be displayed on this diagram. Graph number 1. This is a graph which I am drawing. This is called a geotherm. What is a geotherm? Now, as you start from the Earth's surface and drill a hole, as you go deeper down, the temperature increases. Now, this increase of temperature is non-linear. So, essentially, what we are doing is dP by dt at constant T. That is what is a geotherm. So essentially, geotherm is a isochronous. That means same time. Same time. Is an isochronous PT array that describes the changing temperature with pressure in the Earth's surface at a particular place. Have you understood? So essentially, the geotherm is an isochronous array of points which describe the changing temperature with depth in the Earth at a particular place. So the geotherm here will not be the same as the geotherm in the Atlantic Ocean. They would be different. So this is what is called the geotherm. Now, while I am saying that this is a geotherm, the PT curve of a geotherm can be changed because of processes that operate in the Earth's surface. Because of processes, these are called tectonic processes that operate in the Earth's surface. Its position is not fixed. Its position can be changed given if you can change the heat source, if you can decrease the pressure, there can be many ways to change the position of the geotherm. This is one graph that is important to understand. There is another graph. This is called melting temperature, the melting curve. The melting curve. So here it's solid at lower temperature, or this is further up, and this is melt. And here in this part it is rock / mineral plus. So this is how a melting curve looks like. So you have the geotherm and you have the melting curve. The melting curve separates the solid or minerals to the lower temperature and melts form at high temperature, but the transition is not very sharp across the PT field. It occurs over a temperature interval where you have both rocks and melts in equilibrium. We will talk about it. But right at the moment, you please accept what I am saying, that you have a solid and you have a melt, and then in between that there is a band-like material where you have rock and minerals in equilibrium to the melt. This line, just see this line? It is called the liquidus. We will come to this later on. Liquidus. And this line here is called the solidus. What is it? The liquidus, you can see, at temperatures above the liquidus, it's all melts. So it's melts saturated. At temperatures above this liquidus, everything is a melt. So the system is saturated with melts. And this line here, as you can see, this line, this is called the solidus because at temperatures lower than this, there are only solids, no melts. So this is called a solid saturation line, or in the old Latin, this is called the solidus, and this is called the liquidus. We in geology use the term solidus and the liquids. People in metallurgy, they will use the term liquid saturation line, solid saturation line. We use the term liquidus and solids. Liquidus is the line at temperatures above which everything is liquid. And solidus is the line below which, at all temperatures, the rock is solid. So, we have the geotherm, we have the melting curve, and we have the solid plus melt in its band, and then you have melts. This line is the liquidus, this line is the solidus. And this is the geotherm, as we call it. It's an isochronous, you see T is constant here, isochronous PT array of the changing temperatures with depth at a point in the earth. And this can change from place to place, and even these can change because of a particular tectonic process that may operate. So these are not, the isotherm is not an unique line. So I draw the diagram once more. I'm not labeling them here because you know it, so I'm not labeling. Now you see, the geotherm is at temperatures, normally is at temperatures within the solidus temperatures. That means, normally a geotherm would be in the solid part. It would not go into the melt part. Just for your information, I am drawing another geotherm, an hypothetical geotherm. Here. This is another geotherm. Now you see what is happening. Till here, till this point, the temperature of the earth till this depth is lower than the melting temperature of the rock. So the rock will be solid. Above this temperature, you can see, the geotherm lies in the melt field. So if this happens, then the rock will melt. So, at this depth, above this depth, mark here, above this depth, for this graph, for broken graph, above this depth, the rocks are solid. Below this depth, the rocks are molten. if the geotherm is the broken line. But if the geotherm is a solid line, then you see for all pressure temperature changes, the rock does not melt. Have you understood? This is quite simple to understand, I believe. That for this geotherm, the broken one, above this pressure or depth, rocks don't melt because the geotherm temperatures at till that depth are lower than the surface. But below this depth, the temperature of the geotherm is more than the melting temperature. So the rock, if you take the solid continuous geotherm, you can see the geotherm does not intersect the melting curve and lies to the low temperature. If so, if this is the geotherm, there will be no melting in the rock at all. I hope you get it. Now let's see, we will take another point here. So what we have done in the last diagram that I just erased, I kept the melting temperature curve, did not change the melting temperature curve. I didn't change the melting curve. But I showed two situations of the geotherm. I will do now just the opposite. I will now not change the geotherm, but I will change the melting temperature. And here is the result. Temperature, pressure, that's the geotherm, and this is the melting curve. This is the melting curve. Right? And this is the geotherm. Right? Now let's say you have heard, and we will do this in great detail in the next lecture. Say, if you add a solute to a melt, what will happen? It will cause reduction in the melting temperature. If you have forgotten it, it doesn't matter. We will take it up in the next class. But for this class, if you add a solute, it will reduce the melting temperature. Say, for example, when you melt gold, you add a little bit of something in it so that the melting temperature decreases. Well-known fact. So you add a solute, the melting temperature decreases. So now, this is the melting temperature, and I can draw another melting temperature curve here. How do I bring it here? By adding a solute. There can be other ways, but for the moment, adding a solute, I bring down the melting temperature by a specified amount. Well, look what happens. For the broken line, remember here, for the continuous melting curve given here, the geotherm is at lower temperatures, so no melting. No melting. If you have this melting curve and this is your geotherm, then the geotherm is at temperatures below the solidus. So no melting occurs there. But if you add a solute and your melting curve shifts to lower temperatures, then you have a situation. What is the situation? Look at this point. For this point, you can see the temperature of the geotherm of the earth at a particular point in a particular depth, say P1 till this depth, the melting curve has a temperature lower than the solidus of the contaminated melt. Yes or no? So, no melting for this. But, if you take this depth, then you can see that the geotherm, the temperature of the earth at the depth below P1 is higher than the melting temperature of the contaminated curve. So what will happen? It will be melted. So till P1 there will be no melting in the rock, but below P1 there will be melting. So we come to a very, very important conclusion. Conclusion is that for a particular geotherms are normally at temperatures lower than the solidus, so normally you don't trigger melts. But I will give you a question here. I will ask you the question and you find out the answer. And this is very relevant to this question, and for understanding it, you do not need any special inputs from me, other than what I have said. Now, you know from my earlier lectures that the outer core of the Earth, that is between a depth of 2,900 to 5,100 kilometers, outer core is molten. It's made up of iron and nickel, and it's molten. But inside, where you have the inner core, it's salt. And above it, it's salt. So what we have in the Earth is a sandwiched melt layer of iron-nickel alloys within the Earth. My question to you is, you need to find out why, and you write it down, why does this happen? In very simple terms, not in very complicated ways. In very simple terms, why is the outer layer molten, whereas the mantle and the lower core not molten on the Earth's surface? Although let's assume that the inner core and the outer core have similar compositions, being iron-nickel alloys. You please try to address this question. So now, we have come to an important conclusion. Normally melting is not a standard process to happen because geotherms occur at temperatures normally lower than the solidus temperature. So melting is not frequent in Earth. But anyway, we see volcanoes, we see plutonic rocks, so obviously melting occurs. Now we find out that melting, yes, can occur by two ways. One, you reduce the melting temperature of the rock. The second case that we saw, reduce the melting temperature of the rock by adding a contaminant or a solute, or by shifting the position of the geotherm so that it intersects the melting curve. Geometrically looking, you can either shift the melting curve to lower temperature by adding a contaminant, or by changing the position of the geotherm so that the geotherm intersects the melting curve. It would be an interesting case this is the melting curve, and this is the geotherm. And look at this part. Look at this part. Here, the geotherm, this is the geotherm. The geotherm has higher temperature than the melting curve. So you will produce melts in these zones. But below and above, you won't melt the rock. So essentially, have you understood? Above this, no melting. Below this line, no melting. But between these two lines, the geotherm occurs as a higher temperature at any depth, as a higher temperature than the melting point. So the trigger melting. And when you produce the melts being lighter than the rock would tend to move up. The melts that you produce because they have lower densities, they would start migrating up. So, how do rocks melt? Rocks melt either, normally rocks will not, but because the geotherm is mostly lower than the melting curve, except for the outer core molten thing which I asked you to read about. But one can trigger melting, the earth can experience melting if the melting curve intersects the geotherm. And this can be done by two processes. One, by reducing the melting temperature of the rock, by contaminating it or adding it a solute, or by shifting the geotherm so that it intersects the melting curve. And you can operate from both ends also. You can operate from both ends also. We will see how this works, but for the moment, I will stop here. We will continue with this discussion in the next.